in the group 7. I'm following the Roman numbers, group 7. And because chlorine belongs to group 7, you can fairly say that any other elements that are grouped as one type of elements, like we said that previously, periodic table mainly going to be divided into metals, non-metals, and metalloids. You can trust that a similar category elements in the same group will show similar chemical and physical properties. So that is why, because chlorine is from group 7, you can confidently say that fluorine, bromine, and iodine should exhibit similar chemical and physical properties to that of chlorine. I'm going to limit myself to just fluorine, bromine, and iodine because astatine is some other textbooks, it will be labeled as a metalloid in some textbook most of the times. So it's not in here, but in general it is labeled as metalloid, not in this particular periodic table. So you cannot trust astatine to act very much similar to a non-metal because it happens to be a different type of material, matter. So at least you can confidently say that fluorine, bromine, and iodine are going to act very similar to chlorine. So I'm going back to lecture again. So that should be your answer. So this is the currently approved modern periodic table that we have been using it for at least last 100 years, basically, which is rearranged after initial proposal of Mendeleev's periodicity of elements, which is based on atomic masses, not based on atomic number. But this one is based on atomic numbers, which is approved more than 100 years ago and still is going to be approved because this is the most accurate way of describing elements in a periodic table. And here I want you to pay attention about two numbers. One is on top of the group, on top of the element, and another one is on left side of the periodic table, far left side or right side of the periodic table. So some textbooks or some periodic tables are lazy. They forget to give these numbers, but they were highly useful as well. So this is called a group 1, this is called a group 2, and pay attention to the element, pay attention to the letter symbols. They were labeled as A, and again you have a label A found here, so 3A to 7A. And here you have from 1B, 2B to total 10B, and for different reasons we are going to talk about them later. So here we're going to speak about why they were labeled as A. They were called main group elements or representative elements of the periodic table. In other words, they do not have a d orbitals. When you write the electronic configuration of any one of the element from group 1A to until 7A, you can find that they do not have d orbitals in them. D orbitals containing elements are grouped in the middle, in the blue circle that we are going to speak about them in a couple of minutes. So main group elements are usually special and different from the box inside the periodic table here, inside the periodic table here, and these. So this is mainly spoke about main group elements. These are main group elements. Let me highlight them. These. Okay. And another category is noble gases. Noble gases also do not have d orbitals, but we highlight them especially because they are noble and they have entirely different priorities when it comes to bonding, like we discussed before. Just because they happen to have completely filled electron configuration of the shell that they outside has, so they were not interested in bonding, so we just highlight them specifically. Otherwise it is also part of main group elements. And inside you have transition metals or elements. they were here, excluding this row that contains zinc, cadmium, mercury, and other element. So these are specifically arranged because they have a completely filled d orbitals, but the rest of the elements do not have completely filled d orbital electronic configuration. So the ones that do not have completely filled electronic configuration of d orbital are called transition metals. They were from group 1b to 3b. Sorry, 1b, 3b, and 2b to 11b. And we have lanthanides and actinides that have f orbitals. So in a periodic table, you can see that these has s orbitals, these has p orbitals, and they have d orbitals, and these have f orbitals. Okay. So before I jump onto the next slide where we are going to speak about electronic configuration independently again, I just want to highlight what is the importance of these numbers that you see here. Okay. These numbers here are basically equal to the shell number. Shell number, like shell 1, shell 2, shell 3, shell 4, shell 5. So there are total of 7 shells. You can confidently say that based on this information, you can say that hydrogen has electrons in just shell 1 because that number is projected right next to hydrogen and helium. And you can confidently say that all of these elements here are only found in shell 2, nowhere else. And you can say that all the electrons here are only found in shell 3. I mean outside electrons. That is how you can use it. Okay. So here we are going to spoke about, we just said that noble gases have completely filled electron orbitals. So we are going to apply the periodicity of the elements in periodic table with the electronic configuration of the elements. So we understand how as the element from shell 1 to shell 2 is going, however, they still have similar electronic configuration because the way periodic table of elements is arranged is to have all elements to have similar chemical properties and physical properties. They can only have those similar chemical and physical properties if they happen to have the similar electronic configuration. So here what we have is just an example of a group 1 element and comparison to example of group 1,2 element, group 2a element. So in a group 1, you have a lithium, a first metal. You can say that it has a total 3 electrons, and the first 2 electrons are in 1s2, and that last electron is in 2s1. However, if you have an electronic configuration that is equal to any one of the lower shell noble gas, then you can replace that entire electronic configuration, like in this case of 1s2, with this helium. Whereas for sodium that contains total 11 electrons, the left side you can find that it has the neon as the lower shell noble gas. So we are replacing the 10 electronic configurations with the neon. For potassium, you are replacing for its total 19 electrons. We're saying that it is having argon to the left of it in the periodic table. So you're replacing total 18 electron configuration with the noble gas argon. So you can similarly do that for any element in the periodic table. So just one more example, that is for group 7a, that you can again say that you can replace entire electronic configuration of a noble gas for any element if that element is at least having at least 3 electrons. From lithium you can start do that. For hydrogen you cannot do it because hydrogen has no previous element because hydrogen is the first smallest element in the periodic table. So why we are able to do that is the noble gases have completely filled electron orbitals, sorry, completely filled electron shells, which sometimes we use a word called core electrons to represent it. A core electron means that shell is mostly impenetrable. You cannot add more electrons, or it is hard to remove electron from that shell. So we are going to call it as core, or synonym with strong. So that shell is strong because it is completely filled and perfectly balanced with its charges between electrons and the attractions from the nucleus. So we are going to use the word core to refer to a shell that has a completely filled electronic configuration. So those core is equal to noble gases, because we know that noble gases have completely filled electronic configuration of the elements for that particular shell. Okay, let's see what do we have here. So the question is saying, without using periodic table, give the ground state electronic configuration and a block designation SPDRF block of an atom with A 17 electrons, 37 electrons, and 22 electrons, and classify each atom as a main group element or transition metal. Remember, in a couple slides ago, we discussed what are main group elements. You can find them in the periodic table in the taller groups, 2 on the left side and 6 on the right side. Inside of those taller groups, you find a small block that we call them as transition metals. So the question is asking you to give the electronic configuration for an element with 17 electrons, 37 electrons, and 22 electrons, then find them with the labels of either main group or transition metal. So if you need to, use periodic table, but try to use the one that do not have electronic configurations included in those periodic tables, because it just takes away the thinking from you. So in order for you to do write electronic configuration of any element, first of all, I want you to make your own electron flow chart and make it as a habit, so that you will have the long-term memory that you could use it not just in this entire year of general chemistry, but in future, or maybe even if you take some competitive exams, you could use that. So this is the electron flow chart that we discussed about. We said that for different shells, they have a different number of subshells. So once you have it, you can write your own flow chart of electrons filling from a top right corner to the across. So for 17 electrons, how you do it is, because we already know that what is the capacity of each subshell to accept the electrons, the capacity of s orbital to accept electrons is, s is going to take maximum of 2 electrons, and p is going to take maximum of 6 electrons, and d is going to take maximum of 10 electrons, and an f orbital is going to take maximum of 14 electrons. So because they said 17, you could even start work on this electron flow chart. You can start giving until 17 electrons by giving the maximum electrons possible to the lower shell. So far it looks like I used up 10 electrons and 2 more, 12, and I have a total 17 for the first problem. So I only have 5, not 6. So my electronic configuration of the first element should look like 1s2, 2s2, 2p6, 3s2, and 3p5. Okay. And for element with 37, you can keep going. So instead of stopping here, you can keep going until 37. So I can put 2 here, 2 here, 6 here, 2 here, 6 here. After 6, I need to fill it in 4s and go to 3d10. Looks like I added too many electrons. Let's see how much I left with. So 2 and 2, 4, plus 6, 10, plus 2, 12, and 6, 18, and 10, 28, and 2, 30. So I have 7 more, which means I can give 4p 6 electrons and 4d, not 4d, after 4p 5s1. So my electronic configuration of an element with 37 electrons should end with a 5s1. And if you need to write electronic configuration of an element with 22 electrons, again using this flowchart, you can fill in electrons for the lower shell completely if you are sure about that you have a lot of electrons to start with. Let's see, looks like I have added some amount of electrons, so 10 and 2, 12, and 6, 18, and 2, 20. And after 4s, I need to go back to 3d and add the remaining 2 electrons. So you should be having 22 electrons and end the electronic configuration with 3d2. So how do you find whether it is going to be a main group element or transition metal is by checking the electronic configuration of the last orbital. So in here you have a p orbital. So p orbitals belongs to main group elements, just like s orbitals belongs to main group elements. Here electronic configuration ends with s orbital. Again, they belongs to main group elements. Main group elements. However, in this case, you will find the electrons in d orbital at the last, which are only dedicated to just transition metals. So using the electronic configuration, you can predict where you can locate that element in the periodic table, mostly by looking at the, not mostly, exactly by looking at the last electrons that are placed around the atom. Okay. Hope you had a good understanding of these topics and the electronic configuration and how to find an element location in the periodic table based on its outer shell electronic configuration of the element